In this video, we're interested in factoring polynomials that have complex zeros. So we're going to have two results that we're going to mainly use and see examples of in this video. The first result is that every polynomial of degree n greater than or equal to 1, so this is a general polynomial, with complex coefficients has at least one complex zero. Okay, and note that real numbers are themselves complex. So basically when you can always, you're always guaranteed that every polynomial that's not just constant has at least one zero. That zero is a complex number. Okay, and then also the second result that we're interested in is this, and this is the main result. There exist complex numbers a, c1, c2 to cn, such that any polynomial can be written in this form. A is a constant, it's just a complex number. And then you have x, which is just x to the first power, take away a complex number c1, x take away another complex number, all the way down to x take away an nth complex number, c sub n, where the c1 through cn's are the zeros of the polynomial, okay? And that is actually an extension of the factor theorem, which we saw a video on. So basically the strategy is that you find the zeros of your polynomial, and once you do that, x take away that given zero is a factor of that polynomial, okay? And that's a strategy we're going to be using in this video. Let's see some examples of this. So let's take this polynomial x cubed minus 3x squared plus 4x minus 12. So we're going to do two things. We're first going to find all the zeros of the polynomial, and the second thing we're going to do is we're going to find the complete factorization of that polynomial p. So for part A, you take your polynomial, p of x equals x cubed minus 3x squared plus 4x minus 12, and you begin factoring any way you can. So here I can see that I have four terms, and I can use factoring by grouping. So I'm going to factor out x squared, so it's x squared times x minus 3 plus 4 times x minus 3, and I factor out that x minus 3, that's x minus 3 times x squared plus 4. Okay, now at this stage, what I'm trying to do, remember, I'm trying to find the zeros of this polynomial. So I can see one zero, that is when x is equal to 3, but how do I find the zeros of x squared plus 4? So off to the side, I'm going to set that equal to 0, x squared plus 4, and I'm going to look for the zeros of that. So remember, when you're looking for the zeros of something, you set it equal to 0 and find when it is 0. So in this case, solving this, I have x squared is equal to negative 4. So I get x is equal to positive or negative the square root of negative 4. So x equals positive or negative 2i. Now, positive 2i and negative 2i are therefore the zeros of this. And by the factor theorem, that means x take away 2i and x. So what that means is that the factors x minus 2i, so x take away the first zero, and then x take away the second zero, so x minus negative 2i, that these are both factors of x squared plus 4. That's what the factor theorem says. It says that you take the zeros and x take away the zeros are factors of that polynomial. So I can go back and write this as x take away 3, and then x squared plus 4 can be written as x minus 2i, and then the next one's going to be x plus 2i, so x plus 2i. So to answer the question, my zeros, right, all the numbers that, the complex numbers that cause the polynomial to be 0 would be 3, let's try that again, so 3, and then positive 2i was a zero of x squared plus 4, and then negative 2i was also a 0, right? So that's my answer for part A. Let's box that. And then for part B, what you do is you use your zeros to write the polynomial in factored form, actually, as I did here. So the polynomial can be written as x, a product of factors where it's x take away the zeros. So x take away the first zero, x take away the second zero, and then finally x take away this third zero, x take away negative 2i, so it's actually x take away 3, x take away 2i, and then x plus 2i, which is what I did up there, but I could have saved that down here because that's my answer for part B. Okay, so a couple things about this. The first thing is that the zeros here, the positive 2i and the negative 2i, those are called complex conjugates. So conjugates. So you get conjugates of complex numbers when you have a plus bi and you simply switch the sign in between them, a minus bi. So when you change the sign of the imaginary part, that's taking the conjugate of that complex number. And the first thing I see is that the conjugate pairs, positive 2i and negative 2i, the conjugates, they both appeared as zeros. Okay, and that's not a coincidence. That's always going to be the case where complex zeros with imaginary parts, they come in conjugate pairs. So if you get a plus bi, you're also going to get a minus bi. The second result is that, do you see how the zeros of x squared plus 4 were not real? That is, they had an imaginary part. That tells you that x squared plus 4 is what's called an irreducible, let's try that again, irreducible quadratic. So irreducible quadratic. We say a polynomial, x squared plus 4 in this case, is an irreducible quadratic if the zeros of that polynomial are not real. That's the meaning of an irreducible quadratic, okay? So I ended up factoring and getting a linear term times an irreducible quadratic, okay? And now that irreducible quadratic can be factored further using imaginary complex numbers with imaginary components. Okay, but we're going to address this issue at the end of this video. Let's try another one like this. So let's let the polynomial p of x be equal to x cubed minus 2x plus 4. Once again, let's find the zeros and also the complete factorization of that polynomial. Okay, notice that I can't factor by grouping, right? So we need another factoring technique. Here we're going to use what's called the rational zeros theorem, which we've covered in a previous video. And when you're looking for rational zeros, what you do is you take factors of the constant. So the factors would be 1, 2, and 4, and you divide them by factors of the leading coefficient. The leading coefficient is just a 1. So when you take all those possible quotients, you get 1 over 1, or just 1. So we're going to consider positive and negative 1, positive and negative 2, and positive negative 4. Okay, and if you need to go back and review that video, go ahead and do that now. It's the video on the rational zeros theorem. So you're going to test these numbers, positive 1, negative 1, positive 2, negative 2, positive 4, negative 4. So let's start with 1. So we're going to use synthetic division, testing 1. And I write the coefficients. I have a 1, a 0 because there's no x squared term, a negative 2, and a positive 4. So bring down the 1. It's a 1, 1, 1, negative 1, negative 1, and a 3. Because the remainder is not 0, that means 1 is not a 0 of that polynomial. Let's try 2. So trying 2 with the same coefficients, 1, 0, negative 2, and 4. I have 1, 2, 2, 4, 2, 4, and 8. Once again, the remainder is not 0. Let's try negative 2. So if I try negative 2 to see if negative 2 is a 0, 1, 0, negative 2, and 4. I have 1, negative 2, positive 4, positive 2, negative 4. Okay, so finally I have a remainder of 0, and that means negative 2 is a 0 of this polynomial. That means the polynomial p of x can be written as x take away that 0, so it's x plus 2, right, times the quotient that you get, which is given by these coefficients. X squared take away 2x plus 2. X squared take away 2x plus 2. Okay, now I have this factored down to a linear term, but this is a quadratic. Now, we're not sure if it's an irreducible quadratic yet because we don't know if the zeros are real or not, but I'm going to go ahead and use the quadratic formula on that. So I'm looking for the zeros of this. So I use the quadratic formula, x squared minus 2x plus 2 equals 0, and let's see, what do I get? I get, well, x is equal to 2 plus or minus the square root of 4 minus 4, and a times c is 2, all over 2 times a, which is 2. So I get 2 plus or minus the square root of 4 take away 8, which is negative 4, over 2, which is 2 plus or minus 2i over 2. So I get 1 plus or minus I, because remember the 2 divides into both of those. So I see once again that I have zeros that are not real, right? Because they have that imaginary component, and they occur as conjugates. I have 1 plus I and 1 minus I. So the first part, part A, to answer the question, the first thing I can do is say what my zeros are. Negative 2 is a 0. 1 plus I is a 0. And then 1 minus I is a 0 as well. So that's my answer to part A. And then for part B, to find the complete factorization, what you do is you simply take away all of those zeros and multiply those together. So P of x is equal to x plus 2, and then x take away 1 plus I, so x take away 1 plus I, and then times x take away 1 minus I. And then if you distribute the negative, you end up getting this. P of x is equal to x plus 2 times x minus 1 minus I times x minus 1 plus I. Okay, and that is the complete factorization of this polynomial. Okay, so now once again, notice that we got to a stage where we had a linear factor, and in this case I would call this an irreducible quadratic, because I ended up getting zeros that were not real upon factoring. Okay, so let's go ahead and write these two results down that we've been using. The fact that we get irreducible quadratics, times linear factors, and also that the zeros come in, if you do have complex zeros with imaginary components, that they occur in conjugate pairs. Okay, so the theorem is this, or the two theorems are this. The conjugate zeros theorem, that if the polynomial has real coefficients, so we're only in our class dealing with polynomials that start off with real coefficients, then anytime you have complex zeros, they always occur in conjugate pairs. You always get 2. If you know that, if you end up getting a 0 with an imaginary component, you're always guaranteed to get the conjugate of that as well as a 0. And the second theorem is this, is that whenever you're factoring over the real numbers, that every polynomial with real coefficients can be factored into a product of linear and irreducible quadratic factors with real coefficients. Okay. Now to solve that, or to find the zeros of that irreducible quadratic, we use the quadratic formula as we did in these previous examples. Okay, so in the next video we're going to put this all together, and we're going to end with the fundamental theorem of algebra. Pretty exciting. All right, until next time.